what's the most powerful thing in the universe. In the silent dark between the galaxies, there is no wind, no sound, no air to carry a whisper. Yet here, in the vast ocean of nothing, forces are at work so extreme they can tear apart stars, twist space and time into impossible shapes, and light up the cosmos with energy beyond imagination. Tonight, we will embark on a journey across scales from the tiniest particles dancing inside the atoms of your body to cataclysms so large they can be seen from the edge of the visible universe. We will search for the answer to one question: what is the most powerful thing in the universe? Perhaps it lies in the heart of a dying star, collapsing under its own weight until even light cannot escape. Or maybe it exists in the strange, invisible energy pushing galaxies apart faster and faster. It might not be a place or even an object, but a force woven into the very fabric of reality, a power that has shaped everything from the first moment of creation to this very second. To find it, we must travel across billions of years of history. We will stand on the surface of stars hotter than 1,000 nuclear bombs exploding every heartbeat. We will dive into black holes, where space falls in on itself and time slows to a crawl. We will witness collisions that can forge mountains of gold in a single moment. Our journey will take us from the quantum realm's smallest and the smallest speck of dust to the unimaginable scale of the multiverse, where entire universes may be born and die like sparks in a cosmic fire. And when we return, perhaps we will understand that power is most only about destruction. It is also about creation, the quiet, patient work of building stars, worlds, and life itself. So let us begin. When we speak of power in the universe, we often think of explosions, bright flashes, roaring destruction, the kind of events that can be seen across light-years. But the most fundamental powers are not loud. They are silent, invisible, and constant. They are the forces that have been shaping reality since the first fraction of a second after the universe began. Physicists tell us that everything in existence is governed by just four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Every star, every planet, every atom, every heartbeat you have ever felt is the result of these four powers working together. Gravity is the architect of the cosmos. It pulls matter into clumps, shapes planets, builds stars, and sculpts galaxies. It is the weakest of the four forces, yet its reach is infinite. Gravity never turns off, and it acts on anything with mass. Over billions of years, this quiet pull can create structures the size of galaxy clusters, each containing trillions of stars. Electromagnetism works on a smaller scale, the realm of atoms and molecules, and its influence is everywhere. It binds electrons to atomic nuclei, gives shape to the chemical bonds that make life possible, and powers the light of the sun through the interaction of charged particles. It is 1030 times stronger than gravity, yet it balances itself so perfectly that large objects like planets and people feel no net electric charge. Then there is the strong nuclear force, the most powerful force we know. It binds protons and neutrons together inside the nucleus of every atom. Without it, atomic nuclei would fly apart instantly, ripped apart by the repulsion of their positive charges. This force acts over distances so tiny, less than a femtometer, that is impossible to imagine in our daily experience. And yet, within that tiny range, it is absolute. It is the reason the matter in your body is stable, the reason stars can burn, and the reason nuclear fusion can light the universe. Finally, the weak nuclear force, a misnamed power, because while it is weaker than the strong force, it is essential for the chemistry of the cosmos. It governs radioactive decay, changing one type of particle into another, and in doing so, it shapes the evolution of stars. Without it, the sun could not produce the balance of elements needed for planets and life. These four forces are the foundation upon which all cosmic power is built. They are the invisible scaffolding of reality, the constant, tireless engine behind every event that will follow in our story. But to truly understand what power means in the universe, we must look beyond the quiet forces that hold reality together. They must witness what happens when those forces are unleashed, when the energy locked inside matter bursts free on unimaginable scales. And for that, we begin our journey with the death of stars. Stars are not eternal. They are born, they live, and eventually they die. And when they die, they can unleash energy so vast that, for a brief moment, they outshine entire galaxies. Most stars end their lives quietly. Our sun, for example, will expand into a red giant in about 5 billion years, shed its outer layers, and leave behind a white dwarf at December that will slowly fade into darkness. No explosions, no fireworks, just a long, slow goodbye. But the most massive stars, they choose a different ending. When a giant star, dozens of times more massive than the sun, exhausts its nuclear fuel, gravity takes over. The outward pressure from fusion disappears, and the star's core collapses in a fraction of a second. The outer layers, no longer supported, come crashing inward only to rebound violently when they hit the incompressible core. This rebound creates a supernova, an explosion so bright it can outshine a billion suns. In that single moment, more energy can be released than our sun will produce in its entire 10 billion year lifetime. The blast hurls newly forged elements, gold, silver, uranium, into space, seeding future planets and, eventually, life itself. Without supernova, there would be no Earth, no living creatures to wonder about the stars. But there is an even more extreme death, the gamma-ray burst. These are the most powerful explosions known to occur in the universe. They are not just bright, they are lethal. The gamma-ray burst can release in a few seconds as much energy as our sun will emit over its entire existence. If one occurred within a few thousand light-years of Earth, it could strip away our planet's atmosphere in minutes. Some gamma-ray bursts come from the collapse of truly massive stars into black holes. Others are triggered by the merger of two neutron stars, the ultra-dense remnants of previous supernova. When these stellar corpses spiral into each other, the collision sends ripples through space-time, gravitational waves, and a blinding jet of energy that can be detected across billions of light-years. In October 2022, astronomers detected a burst so intense they nicknamed it the BR8, the brightest of all time. Its light had traveled for over 2 billion years before reaching Earth. Yet, it was powerful enough to overwhelm our detectors. Events like these are rare, but they remind us that the universe is capable of sudden, violent acts on scales we can barely comprehend. And yet, as powerful as supernova and gamma-ray bursts are, they are just the opening acts in the cosmic theater. For beyond them lie forces that do not merely destroy stars, they swallow them whole, bending the very geometry of space and the flow of time. To find them, we must journey to the edges of gravity's dominion, to the most extreme objects ever discovered, black holes. Black holes are not merely massive objects. They are regions of space where gravity has won, where it has crushed matter into a point so dense, so compact, that nothing, not even light, can escape. Imagine the Earth compressed down to the size of a marble. Now imagine the sun reduced to a sphere only a few kilometers across. That is the kind of density we are talking about. At the heart of every black hole is the singularity, a place where our current understanding of physics breaks down. Around it lies the event horizon, the point of no return. Cross it, and you are gone, not just physically, but causally. No signal, no message, no particle can ever return to the outside universe. Black holes come in sizes ranging from a few times the mass of our sun, the remnants of massive stars, to supermassive black holes weighing billions of solar masses, lurking in the centers of galaxies. The largest ever found, TON 618, is estimated to have a mass of 66 billion suns. Its event horizon would engulf our entire solar system. Despite their reputation as cosmic vacuum cleaners, black holes are not empty, silent voids. When matter falls toward them, it forms a swirling accretion disk, a flattened whirlpool of gas, dust, and even entire stars, spiraling inward at nearly the speed of light. Friction and magnetic fields heat this disk to extreme temperatures, causing it to blaze with radiation so intense it can be seen from across the universe. And then there are quasars. A quasar is a supermassive black hole in the act of feeding, devouring matter at such a furious rate that it can outshine its entire host galaxy. Some quasars emit relativistic jets, beams of particles launched from the edges of the accretion disk at almost the speed of light, stretching for millions of light-years into intergalactic space. The energy output of a single quasar can be thousands of times greater than all the stars in the Milky Way combined. If our Sun were replaced by a quasar of equal mass, Earth would be vaporized in an instant. Black holes are the ultimate expression of gravity as power. They do not just warp space, they warp time itself. Approach a black hole, and seconds for you may be years for an outside observer. Fall in, and your journey ends, but your image, frozen at the event horizon, would linger for eternity. And yet, for all their violence and mystery, black holes are not the final word in cosmic power. There is a force working quietly in the background of the entire universe, shaping its fate, pushing galaxies apart faster and faster, and threatening to tear the cosmos itself apart. It is not fire, it is not matter. It is something far stranger, a power without a face, without a center, without a limit. It is dark energy. For centuries, we believed gravity was the dominant force shaping the cosmos. It pulls planets around stars, stars into galaxies, and galaxies into clusters. Its influence is infinite, and its grip, we thought, was unbreakable. But the universe holds a deeper secret. In the late 1990s, astronomers studying distant supernovae expected to see the universe slowing down under gravity's pull. Instead, they found the opposite. The expansion of the universe was speeding up. Something was pushing galaxies apart, overcoming gravity itself. We call this mysterious driver dark energy. We do not know what it is. It does not shine. It does not seem to interact with matter at all. And yet, it makes up nearly 70% of the entire energy content of the universe. Think about that. Almost everything that exists is made of something we cannot see, cannot touch, and cannot fully describe. The best we can do is measure its effect. Over the past 5 billion years, dark energy has been stretching space faster and faster. If it continues unchecked, the distant galaxies will drift so far away that their light will never reach us again. One day, the night sky could be nearly empty, save for the stars of our own galaxy. And then there is dark matter, another invisible force, making up about 27% of the universe. Unlike dark energy, dark matter does not push, it pulls. It holds galaxies together, providing the extra gravity needed to keep stars from flying apart. We cannot see dark matter directly, but we can map it through its gravitational lensing, the bending of light from distant galaxies as it passes through massive clouds of unseen matter. In some galaxy clusters, the dark matter outweighs the visible matter by a factor of 5 or more. Together, dark energy and dark matter form the hidden skeleton and pulse of the cosmos. They determine the shape of space, the motion of galaxies, and perhaps even the ultimate fate of everything we know. But even these invisible giants are not the strangest things the universe has to offer. For in the depths of space, there are objects so bizarre, so exotic, that they seem to defy our understanding of physics. Remnants are still a death and the possible echoes of the universe's earliest moments. To meet them, we must look toward the exotic cosmic monsters, neutron stars that crush atoms flat, magnetic titans that could erase your mind from across half the solar system, and hypothetical structures born in the first heartbeat of time itself. If black holes are the kings of gravity, then neutron stars are the jewel-encrusted night, small, deadly, and impossibly dense. A neutron star is the remnant of a massive star that has gone supernova, but was not quite massive enough to become a black hole. In the collapse, the star's core is squeezed so tightly that protons and electrons merge into neutrons. The result is an object about 20 kilometers across, roughly the size of a city, yet containing more mass than our Sun. 1 teaspoon of neutron star material would weigh about 4 billion tons more than Mount Everest. Its surface gravity is 200 billion times stronger than Earth's. Drop a marble from 1 meter above the surface, and it would hit the ground at a significant fraction of the speed of light. But neutron stars have cousins even more terrifying, magnetars. These are neutron stars with magnetic fields 1,000 times stronger than a normal neutron star, are trillions of times more powerful than the strongest magnet ever created on Earth. A magnet's magnetic field could strip the electrons from every atom in your body from a distance of thousands of kilometers. A single magnetic flare from a magnetea can release as much energy as the sun emits in 100,000 years. And then there are the hypothetical monsters, things we have never seen, but which physics suggests might exist. One such creature is the quark star. If the collapse of a neutron star goes even further, neutrons themselves might break apart into their constituent quarks, forming an even denser object. A quark star, if it exists, would be so compact that its surface would be just a thin layer of exotic matter, beyond which lies a soup of free quarks, the smallest building blocks we know. Even stranger are cosmic strings, hypothetical defects in space-time itself, perhaps formed in the first microseconds after the Big Bang. These infinitely thin, infinitely long structures, if real, could be heavier than a galaxy per centimeter and might warp space around them so violently that they could create closed time loops. One cosmic string passing through our solar system could unleash gravitational waves powerful enough to shake planets apart. And finally, there is a possibility so chilling it sounds like the plot of a science fiction horror story: vacuum decay. Our universe may be in a false vacuum state stable for now, but not truly the lowest possible energy configuration. If a tiny bubble of true vacuum ever formed, it would expand at the speed of light, rewriting the laws of physics as it went. Atoms, stars, planets, and life would vanish instantly, without warning, and without even the chance to know it had happened. These cosmic monsters, real or theoretical, remind us that power in the universe is not just about size or brightness. Sometimes it hides in tiny packages, waiting in silence, capable of rewriting reality in a heartbeat. But if we want to talk about the most powerful processes of all, ones that create entire universes, forge the first stars, and set the stage for everything else, we have to go back to the very beginning, back to the birth of the cosmos. To understand ultimate power, we must travel back to the first moment of time, not to the birth of stars, or even the birth of galaxies, but to the instant when the universe itself came into being. The Big Bang was not an space, it was an explosion of space. 13.8 billion years ago, all the energy, matter, and even the dimensions of space and time were compressed into a single, unimaginably small point. Then, in less than a trillionth of a second, space began to expand, not at the speed of light, but faster. This brief, furious phase is called cosmic inflation. In this moment, the universe grew from subatomic size to something vast enough to contain all that we see today. If you had been there, you could not have been, because there was no there yet. You would have seen space itself stretching faster than light, smoothing out and cooling as it went. The energy of the early universe was so intense that matter, as we know it, could not exist. Instead, the cosmos was filled with a seething plasma of fundamental particles, quarks, electrons, photons, neutrons. Temperatures reached over 1 trillion degrees, so hot that atomic nuclei could not hold together. As the universe expanded, it cooled, and within minutes, protons and neutrons began to fuse into the first simple atomic nuclei: hydrogen, helium, and traces of lithium. This process, called Big Bang nucleus synthesis, forged the raw ingredients for all future stars. For the next 380,000 years, the universe remained a glowing fog of particles and light, opaque to any direct view. Then, as the temperature dropped to around 3,000 degrees Kelvin, electrons bound to nuclei, forming neutral atoms, light could finally travel freely through space. This first light, the cosmic microwave background, still bathes the universe today, a faint afterglow from the dawn of time. From this moment, gravity began its quiet work, pulling together tiny irregularities in the density of matter, seeded by quantum fluctuations during inflation over hundreds of millions of years. These ripples grew into clouds. Clouds became clumps, and clumps became the first stars. The first stars were nothing like the sun. They were titans hundreds of times more massive, burning with such ferocity that they lived only a few million years before exploding. Their deaths scattered heavy elements into the surrounding space, paving the way for second-generation stars, planets, and eventually life. In those early days, the universe was young, bright, under our place of unimaginable power and constant transformation. And yet, for all its grandeur, the story of cosmic power does not end with creation. Because in the universe, creation and destruction are two sides of the same coin. Both are necessary for the most extraordinary thing we know of to exist, life. For billions of years, the universe was a theater of matter and energy alone. Galaxies collided, stars were born and died, black holes fed in silence. No one was there to see it. And then, on a small, rocky world orbiting an unremarkable star, something remarkable happened. Chemistry became biology. Molecules began to copy themselves, compete, and evolve. Life had begun. From the very start, life faced impossible odds. Meteor impacts could boil oceans. Ice ages could lock the planet in frozen silence. Supervolcanoes could choke the skies with ash. Yet life endured, adapting, reshaping itself to survive every catastrophe the cosmos hurled at it. We often think of power in terms of destruction of explosions, gravity wells, and cosmic forces. But there is another kind of power, the ability to persist, to bend without breaking, to turn chaos into opportunity. Life does not match a supernova in brightness or a quasar in energy output. Yet it does something those titanic forces cannot. It learns. It changes. It remembers. On Earth, life climbed from the oceans to the land, took flight into the skies, and eventually began to look up at the night, wondering what lay beyond. It built tools, then machines, then telescopes that could see the afterglow of the Big Bang itself. And now, life in the form of human curiosity has sent its creations to the moon, to the outer planets, and beyond the solar system, carrying its story into the dark. In a sense, life is the only force in the universe we know of that can look at all the others and say, "I understand you." It can name the stars, measure the speed of galaxies, even imagine the moment before time began. Life can take the raw power of the universe and turn it into art, language, and meaning. And perhaps, when we speak of the most powerful thing in the universe, it is not a black hole or dark energy or the fire of a newborn star. It is the simple fact that we tiny, fragile beings on a pale blue dot can look into the infinite and ask why. But this power comes with a question. Is life's influence a fleeting spark in the dark, or the first hint of something even greater still to come? If life can survive long enough, its power may grow far beyond what we can imagine today. For the universe is vast, and the tools it offers are limited only by knowledge and time. Consider the Dyson sphere, a hypothetical megastructure encasing a star to capture nearly all of its energy. Such a civilization would wield power on a stellar scale, harnessing more energy in a single year than all of human history combined. We have seen hints, strange dimming stars, unexplained infrared emissions, but so far, no confirmed examples. Then there is the Carter's EV scale, which measures civilizations by the energy they control. Humanity today is barely a Type I civilization not yet able to use all the energy available on our own planet. A Type I civilization would command the full output of its star. A Type I civilization would draw upon the energy of an entire galaxy, perhaps moving stars, reshaping galaxies, and even influencing the fabric of space-time itself. Some scientists imagine stellar engineering altering the life cycles of stars to extend their lifespan, or creating new ones from raw gas. Others speak of black hole farming, feeding black holes to use the Hawking radiation as a near-eternal energy source, or tapping the incredible rotational energy locked within their event horizons. And perhaps the ultimate act of power, creating new universes. The laws of physics might permit it, tiny, inflating bubbles of space-time branching off from our own, each with its own constants, its own stars, its own life. A civilization capable of such a feat would not just live in the universe, it would become a universe minus maker. Yet with all this speculation, there is an irony. Even the mightiest galaxy minus spanning civilization would still be subject to the deep recurrence of cosmic time. Stars will burn out. Galaxies will drift apart. The universe may end in cold darkness, heat death, or something stranger still. In that far future, power may not be measured in explosions or luminosity, but in the ability to preserve meaning against the silence, to carry knowledge, memory, and the spark of life across eons, even as the last photons fade. Perhaps then, the most powerful thing in the universe is not a phenomenon or a machine, but a story, the story life tells about itself and the cosmos that made it. A story that began with the first stars, and that may, if we are wise, never truly end. We began with a question: what is the most powerful thing in the universe? We explored the crushing grip of black holes, the silent push of dark energy, the blazing fury of quasars, and the unfathomable birth of space and time. We saw the indifference of neutron stars, the elegance of cosmic strings, the ancient light from the first atoms, and the fragile persistence of life. We looked ahead to futures where civilizations may reshape galaxies or kindle new universes. And still, the answer is not a single object or force. It is not gravity, nor light, nor matter, nor energy. The most powerful thing in the universe is the ability to see it, to understand it, to take the raw chaos of stars and void and turn it into meaning. For without that, the cosmos is vast but silent. With it, even a small mind on a small world can hold the entire universe in thought. Perhaps one day, far from now, when the lost galaxies fade into the dark, there will still be something somewhere that remembers. And in that act of remembrance, the universe will still be alive, because the greatest power is not in shaping the universe, but in knowing it.